So imagine you're just sitting there looking at a screen full of incredibly complex code. Or, maybe it's a dense textbook filled with advanced calculus,
Right.
and your brain just, well, it just completely freezes, like totally locks up.
Oh, yeah. The classic deer in the headlights feeling.
Exactly.
Yeah.
And the weird thing is, you know all the individual words, right? You know what the numbers are, but there is absolutely no movie playing in your head.
Not at all.
Yeah, instead of like a smooth flow of logic, you're just staring at this wall of static, and this very specific, really frustrating paralysis sets in. So if you are listening to this and you have ever felt that, I need you to know right now, you aren't lacking intelligence.
No, not alone.
You are experiencing something incredibly specific. The sources we have today call it simulation drop.
Yeah, and simulation drop is just this phenomenal term from cognitive psychology.
Yeah.
Basically, what is happening in that exact moment of paralysis is that your working memory is actively collapsing. It is just getting crushed under the weight of cognitive overload.
Like your brain's RAM is just full.
Exactly like that. You see, you're trying to use the language processing centers of your brain.
The parts for, like, reading a book.
Right. The parts designed to read sentences sequentially, one after another.
Yeah.
You're trying to use that to process multidimensional concurrent logic, and the human brain simply refuses to do it. It just crashes.
Wow. Okay, so that freezing sensation, and more importantly, how we can systematically cure it, is exactly what we are unpacking for you today in this deep dive.
And we really have an amazing stack of sources for this one.
We do. It's arguably one of the most fascinating collections we've ever gone through. We are basically bridging algorithmic problem solving,
Yeah.
so specifically looking at those brutal coding interviews like LeetCode.
Oh, the dreaded leak code.
Right. We're bridging that with cognitive psychology, educational theory, and then, and this is the crazy part, we're going to trace this exact same mental failure all the way up to high-level mathematics.
We're talking calculus, linear algebra, even stochastic calculus on Wall Street.
Yeah, it's literally a roadmap of how human beings interact with and, well, often completely fail to process sheer complexity. But the best part is, our sources actually provide the antidote.
The antidote is the key here.
The mission for us today is to figure out how to unlock what we're going to call the right brain translator.
I love that term.
It's basically this underlying, almost secretive mechanism that elite performers use. They take dry, terrifying mathematical symbols and somehow translate them into vibrant, moving, geometric realities.
This is how they solve them so fast.
Right. So if we want to understand how to build this translator for ourselves, we have to start where the pain is the absolute worst. We need to go into the trenches of computer science coding interviews. Let's look at a classic problem that reliably causes that simulation drop we were just talking about.
Okay, let's do it.
The notes single out a very specific, totally infamous challenge, LeetCode 153.
Ah, yes. Finding the minimum in a rotated sorted array. That is a legendary stumbling block. Just a complete nightmare for beginners.
It really is. So, for anyone listening who hasn't had the pleasure of sweating through this in an interview room, let's visualize the problem together. Imagine you have a list of numbers, right? And they were originally in perfect ascending order.
Like a normal sorted array.
Yeah. So let's say 0, 1, 2, 4, 5, 6, 7. Simple enough.
Very clean.
But then, before you actually get to see this list, someone takes the first few numbers and just chops them off and moves them to the back. They rotate it.
They break the perfect order.
Exactly. So now the array looks like this. 4, 5, 6, 7, 0, 1, 2. And your task is to write a highly efficient algorithm to find that 0, to find the minimum number.
And you have to do it fast.
Right. Now, the traditional approach, the one that makes everyone absolutely miserable, involves trying to just read that array from left to right.
Which is instinctual.
Yeah, you read it like a sentence, and you try to mentally track 3 different moving targets at the same time. You have a left pointer, a right pointer, and a mid pointer. I actually want to try doing this out loud right now just to see what happens.
Please, go for it. Feel the friction in real time.
Okay, let's do it. So the array is 4, 5, 6, 7, 0, 1, 2. My left pointer is at index 0, which holds the value 4.
Okay.
My right pointer is at index 6, which holds the value 2. Now I need to calculate the mid pointer. So 0 plus 6 is 6, divided by 2 is 3. So mid is index 3.
Still with you.
Okay. What value is at index 3? Let me count from the start. 0, 1, 2, 3. Okay, the value is 7. Now I have to compare that 7 to Wait, what was the value at the right pointer again? Was it 6 or was it 2?
And right there,
Yeah.
the simulation drops. Your brain just fully crashed.
I genuinely lost it. Like,
Yeah.
the numbers literally just evaporated from my head.
Because you are attempting to be a human debugger. You're trying to act like a computer processor. And this actually touches on a fundamental biological limit. It's known as Miller's Law.
Miller's Law, what is that?
In cognitive psychology, it's a generally accepted rule that the average human brain can only hold about 7 out of, give or take, 2 distinct items in working memory at any given time.
7 items total.
Yeah, that's it.
Yeah.
So when you sit there and try to hold the index for the left pointer, the actual value of the left pointer, the index for the right, the value for the right, the calculated index for mid, the value for mid.
Oh my gosh, that's already 6 things.
Exactly. And then you still have to hold the logical rule of the code you're supposed to execute next. You have literally exceeded your biological RAM limit. The system just throws an out-of-memory error.
So if trying to run the code in my head, like that is just a guaranteed biological path to failure, what is the algorithm actually trying to accomplish? Because the sources suggest that the core of this binary search is just wildly misunderstood by most people.
Wildly misunderstood.
Yeah, like it's usually taught as a really simple higher or lower guessing game. Like when you ask a kid to pick a number between 1 and 100.
Right. Is it 50? No. Higher. Framing binary search as a guessing game is honestly an incredible disservice to what the algorithm actually represents. It trivializes a really profound mathematical concept.
So how did the sources reframe it?
They use a much more rigorous term. They call it feasibility partitioning.
Okay, feasibility partitioning. Break
Wow.
that down for me because that sounds like some heavy computer science jargon.
Let's strip all the jargon away. The core abstraction of any binary search isn't about guessing numbers. It is about discovering a fault line.
A fault line, like an earthquake.
Kind of, yeah. You are looking for a single critical tipping point that splits your entire universe of possibilities into a binary true and false state. On one side of this fault line, every single element fails a specific condition. It's all false. And on the other side, every single element satisfies it. It's all true. Your goal isn't to look at the numbers at all.
Wait, I'm not looking at the numbers.
No, your goal is solely to find the boundary between true and false.
Okay, I conceptually grasp finding a fault line. That makes sense. But how does that actually apply to our broken or rotated array, the 4, 5, 6, 7, 0, 1, 2? It really doesn't look like a neat true and false split to me. It just looks like a mess of random integers.
And this is where we have to introduce a massive concept, the invariant.
The invariant.
Yes.
Well, yeah.
An invariant is a property of a system that remains absolutely true no matter how much the system changes, or how much it gets rotated, or how chaotic it appears on the surface.
So something that never changes.
Exactly. If we look at that rotated array and we compare every single number in it against the very last element in the array, which is the number 2, something almost magical happens. A perfect true and false boundary just reveals itself.
Wait, let me actually test that. So our last number is 2. The array starts with 4, 5, 6, 7.
Right.
And all of those numbers, the 4, 5, 6, and 7, they are strictly greater than 2.
Correct. So conditionally, they evaluate to false.
Okay, false, 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 false. Then we hit the rotation point, the cliff. The next numbers are 0, 1, and then the 2 itself. And all of those are less than or equal to 2.
Which means they evaluate to true. Do you see what you just did?
Oh, I think I do.
You no longer have an array of 7 random integers. You've completely removed the numbers from the equation. You have successfully transformed a really complex numerical tracking problem into a pure binary classification problem.
Oh, wow. So my array isn't 4, 5, 6, 7, 0, 1, 2 anymore. It is literally just false, 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 true, true, true.
Yeah.
That is incredibly elegant. So if I pick a middle point, right, and it lands on a false, say, it lands on the number 6, I don't need to know anything else about the rest of the numbers. I just know with 100% absolute certainty that my target, the true values, must be sitting somewhere over to my right.
Yes.
I can just confidently discard the entire left half of the array.
And that right there is feasibility partitioning in action. You aren't guessing. You are systematically collapsing a space based on a universal property. But achieving this elegance requires setting up your code perfectly.
Right.
Which actually brings up a fiercely debated topic in the sources. They call it the dynamic boundary debate.
Oh, yes. I really wanted to dig into this because, honestly, reading it frustrated me. The sources spend a lot of time arguing about how to actually code this true and false check. They insist that when we compare our middle pointer to find out which side of the fault line we're on, we absolutely must compare it to a dynamic moving right boundary.
Yeah, specifically using the variable nums right.
Right. And they aggressively warn against comparing it to a fixed, unchanging endpoint like nums n1.
They do. It seems like a tiny semantic difference, a subtle distinction in syntax, but it represents a massive canyon between how a novice programmer thinks and how a true master thinks.
Okay, but I have to push back here. I have to advocate for my own fragile working memory.
Go for it.
If the array's very last value, nums n1, which is the number 2 in our example, if that gives us that perfect, beautiful baseline that creates the true and false split, why on earth wouldn't I just anchor my logic to that fixed number?
It seems easier, doesn't it?
Yeah. If my whole problem is cognitive overload, isn't a fixed, unchanging target infinitely easier for my brain to track than a right pointer that just keeps shifting around every single time the loop runs?
Your intuition is completely logical. Based on everything we just discussed about reducing cognitive load, a fixed anchor absolutely feels safer. It feels like less work. But relying on that global nums n1 creates a fatal structural flaw in your algorithm.
Fatal how?
It creates a brittle algorithm that just shatters into pieces the moment the environment changes even slightly. Let's actually walk through the mechanics of why that happens.
Yeah, please, walk me through it. Because I don't see the danger.
Okay. Imagine your binary search is working perfectly. It has successfully chopped away the left side of the array, just like we wanted, and now your left and right pointers have narrowed the search space down to a tiny, tiny subarray. Let's say it just contains 3 numbers, 0, 1, and 2.
Okay, so my left pointer is on the 0, right pointer is on the 2. They are localized to just those 3 numbers.
Notice what has happened to this specific little subarray. It is no longer rotated.
Oh, right, because we chopped off the big numbers.
Exactly. The 0, 1, 2 is now perfectly sorted. Now, if your algorithm uses a dynamic right boundary, it looks at the middle value, which is the 1, and it compares it to the dynamic right value, which is currently the 2.
Right.
The 1 is less than the 2. The logic holds perfectly. The code smoothly says, great, I'm in a sorted space. My middle value is smaller than my right value, so the minimum must be somewhere to my left. And it collapses perfectly onto the 0.
That makes perfect sense. The logic works. But wait, wouldn't the fixed boundary do the exact same thing? Because the fixed end of the whole array is also 2.
In this highly specific, very lucky instance, yes, it works. The fixed boundary and the dynamic boundary happen to be the exact same number. But what if you are solving a variation of this problem that includes duplicate numbers?
Oh, okay. Like LeetCode problem 81.
Exactly like LeetCode 81. Your array might look something like this. 1, 0, 1, 1, 1.
Okay, that's a lot of ones.
Let's run it.
Yeah.
If you calculate your midpointer, you land on a 1. Your fixed end anchor, nums n1, all the way to the end, is also a 1. They are completely equal.
So the mid is 1, and my fixed global target is 1.
Now tell me, which half of the array do you throw away?
I honestly don't know. The 0 could be on the left side or it could be on the right side. Both sides are entirely surrounded by 1.
Exactly. You are completely paralyzed. Because you're laid on a fixed external anchor, a number sitting way outside your current little search space,
Yeah.
you have absolutely no way to safely reduce your search area. You're stuck.
Wow.
But let's replay that exact same scenario with a dynamic right boundary. Your mid is 1, and your dynamic right pointer is currently pointing at a 1. Because they are equal, you still don't immediately know which half to throw away.
Right, the ambiguity is still there.
But you could do something incredibly powerful. You could just say to the code,
Right.
right 1. You can just shrink your right boundary inward by a single step.
Wait, why is that safe? What if that rightmost one was actually the minimum? What if we just threw away the answer?
Because you already have another one sitting right there at your midpointer.
Oh.
You are guaranteed not to lose the minimum value because you have a duplicate of it safely held in the middle of your search space. You can safely creep the dynamic boundary inward, just slowly eating away the duplicates from the edge until the 0 finally reveals itself. You absolutely cannot do that with a fixed global anchor.
That is a phenomenal breakdown, really. So if I use a fixed number, I'm making critical decisions from my tiny, localized search space based on a ghost, a number that sits totally outside my current reality.
That is perfectly stated. That is what the sources call violating the principle of locality. Your logic, your true and false checks, must remain perfectly contained within the isolated microworld of your current left and right pointers. If you look outside that microworld, you break the system.
Okay, so we've definitively established the trap of working memory, and we've established the really rigorous logic required to navigate it safely. But how do we actually, see it?
Seeing it is the real trick.
Right, because if holding all these dynamic pointers in our head causes a crash, how are the elite programmers tracking all this without failing? This takes us right into the concept of mental scaffolding and what the notes call the 5-minute no-code rule. How do the top performers visualize a rotated array?
Well, the truth is they do not see numbers. They just don't. They do not see arrays or commas or brackets.
Mm-hmm.
When a master programmer reads the words rotated sorted array, their visual cortex immediately takes over. They instantly project a geometric shape into their mind's eye.
But what kind of shape are we talking about?
They literally see a graph with two parallel diagonal lines. Try to picture it. The first line is drawn high up on the y-axis, sloping upward from left to right. This represents the larger numbers that got rotated to the front of the array.
Okay, floating high up.
And the second line is drawn lower down on the axis, also sloping upward. This represents the smaller numbers that got shifted to the back.
So it's just two floating line segments. That really reminds me of that scene in The Matrix.
Oh, which scene?
At the beginning of the movie, Neo just sees green numbers raining down the screen, right? He's just reading the raw syntax. But by the end of the movie, he doesn't see the code anymore. He looks at the green rain and he just sees the hallway, he sees the agents, he sees the actual physical architecture of the simulation.
That is a neurologically perfect analogy. Top performers literally stop reading the syntax of the code and they start seeing the physics of the problem. If you visualize those two diagonal lines, the logic of binary search becomes completely effortless. If your middle pointer lands anywhere on that upper line, you don't need to do any mental arithmetic. Visually, geographically, the lowest point of that entire system, which is the start of the bottom line, has to be to your right. You don't calculate it. You just look at the geometry. You take a mental pair of scissors, and you just snip off the left half of the graph.
It really feels like an unfair advantage. Honestly, it feels like a superpower. But the sources are absolutely adamant that this is not raw genetic talent. We aren't talking about people born with mutant brains here.
Not at all. It is high-frequency pattern recognition built through very deliberate mechanics, specifically chunking and conditional transfer.
Explain chunking.
Chunking is a well-documented cognitive phenomenon. It's where the brain takes a complex multi-part sequence of information and compresses it down into a single, highly recognizable unit.
Give me an example of that.
Think about reading a word. You don't look at the letters C, then A, then T, and then try to synthesize them in your head. Your brain has chunked those individual shapes into the singular concept of a cat. Top programmers have just chunked algorithmic logic into geometric shapes.
And the incredible thing is, the sources don't just describe this phenomenon, they give us a literal step-by-step training manual for how to build this right brain translator for ourselves. They outline 4 meta habits.
These are crucial.
Yeah, if you were listening to this and you want to stop freezing up on complex problems, whether it's code or literally anything else, this is the exact protocol to follow. Let's walk through these. Meta habit number 1 is schema classification.
Schema classification means you have to fundamentally change how you categorize the problems you face. Most people group problems by their technical jargon. They have a folder in their brain for array problems and another folder for pointer problems.
Right, which sounds logical.
It sounds logical, but you need to throw that filing system away. You must start grouping problems by their physical geometric shapes.
The sources give 2 amazing examples of this. The first is something called the sliding window problem. Now, traditionally, a sliding window is taught as a while loop containing an if statement, incrementing variables, tracking boundaries.
Pure syntax.
Yeah. But the schema classification says, no, don't do that. Visualize a stretching caterpillar moving across a branch.
Let's actually map that metaphor directly to the mechanics because it is brilliant. The head of the caterpillar represents your right pointer. It stretches out, moving forward, consuming new data, expanding the window to see if it can find what it needs.
And it just keeps stretching and stretching until it eats something toxic or breaks a rule.
Precisely. And once the condition is violated, the caterpillar has to contract. The tail of the caterpillar, which represents your left pointer, is forced to pull forward, scrunching the body up, dropping the old bad data out of the window until the condition is safe again.
So when you are actually writing the code, you aren't trying to remember the syntax of a nested while loop. You are literally just coding the physical movement of the head stretching and the tail catching up.
It's exactly.
The second example they give is for something called a monotonic stack. Again, incredibly dense, intimidating computer science jargon.
Yes. A monotonic stack is formally defined as a data structure that maintains elements in a strictly increasing or decreasing order. Again, don't think about the computer science. The visual schema for this is just a line of people of varying heights.
Right. Imagine a single file line of people. If a massive 7-foot-tall person steps into the very back of that line, they completely eclipse and block the view of all the shorter people standing right in front of them. In the physical reality of this line, those shorter people have effectively ceased to exist to anyone looking from the back.
And that physical reality translates perfectly to the code. When a larger number enters the stack, you pop out all the smaller numbers. You physically delete them from the memory structure because they are eclipsed. If you can clearly see the tall person stepping into the line in your head, the code practically writes itself.
Which brings us to meta habit number 2. And I have to say, this one feels really aggressive. It is the 5-minute no-code rule.
It is aggressive.
Yeah.
And it is arguably the single most transformative habit you can possibly adopt. The rule is absolute. For the first 5 minutes of looking at any complex problem, you are explicitly forbidden from touching a keyboard. You are forbidden from writing a single line of code. And you are forbidden from writing down the specific numbers from the prompt.
Okay, but if I can't write code or numbers, what am I supposed to do for 5 minutes? Just stare at the screen.
You must draw. You get a piece of paper, and you are forced to define the problem visually. You draw X and Y axes, you draw the shape of the data, you mark your target with a star, you draw arrows indicating how the pointers will physically move through space.
Wow.
By forbidding your left brain from using its beloved text parser, you are physically forcing your visual cortex to wake up and take complete control of the problem.
I love the friction of that.
Yeah.
You are intentionally disabling the exact part of your brain that wants to fail. It's brilliant. Okay, meta habit 3 is find the property, which ties directly back to what we discussed earlier about invariants.
Yes, invariants are key.
Right. In the chaos of a brand new problem, you need a conceptual anchor, not a numerical one.
A perfect example from the sources is a mountain array. This is an array of numbers that steadily increases to a peak and then steadily decreases.
So visually, a triangle.
Visually, yes, a triangle. And the invariant property, the thing that is universally true, regardless of what the actual random numbers are, is that the left slope always strictly rises and the right slope always strictly falls.
Simple geometry.
Exactly. If you identify that property first, you don't care how high the mountain is or how wide it is or what the data points are. You just build your cutting logic around the fact that climbing means you are on the left side and falling means you are on the right side.
And finally, meta habit 4, retrospective mapping. This is basically the maintenance work, right?
Yes.
This means taking problems you solved weeks ago, maybe problems where you just brute force the code or memorize the answer from a tutorial and you revisit them. But you don't look at the code. You get a blank sheet of paper and you retroactively draw the geometry of the problem.
You strip away every single semicolon, every bracket, every variable name, until absolutely nothing remains but the pure structural shape. This is how you actually build the library of schemas in your brain.
You're doing reps.
You are actively rewiring your neural pathways so that next month, when you see a similar problem, the caterpillar or the mountain just pops into your head automatically.
So we have this incredibly powerful, neurologically sound method for avoiding cognitive overload. It literally turns impossible problems into visual intuition. But this forces a massive, glaring question for me.
Let's hear.
If this right brain method is the definitive key to mastering complexity, why on earth is it kept a secret? Why isn't this the very first lecture in every single prestigious university? Why isn't this the opening chapter in classic, heavy textbooks like Introduction to Algorithms?
To really understand that disconnect, we have to pull back and look at the architecture of computer science education as a whole system. It comes down to a fundamental misclassification of complexity. We need to distinguish between structural complexity and logical complexity.
Let's define those really carefully because that sounds like the exact root of the issue.
Universities and traditional software engineering programs are overwhelmingly designed to teach you how to manage structural complexity. This is the domain of building massive, sprawling systems, things like operating systems or global enterprise applications. Millions and millions of lines of code.
Right, massive scale.
To survive structural complexity, the software industry created something called defensive abstraction.
Defensive abstraction, what exactly are we defending against?
You are defending against the chaos of thousands of human beings working on the exact same project at the same time. Think about how an interface or an abstract class works in programming. These are industrial safety standards.
Okay, give me a real-world example of that.
If you are a programmer writing a feature that processes a credit card payment, you interface with an API. You just write a command that says charge card. You are entirely shielded from knowing how the bank's database is structured or how the physical hard drives in the server farm are spinning.
The abstraction hides the messy details, so my brain doesn't literally explode trying to process the entire internet infrastructure just to charge $5.
Precisely. It is a defensive wall, keeps you safe.
Yeah.
But algorithms, the kinds of things we see in leet code or dense mathematics, do not suffer from structural complexity. They suffer from logical complexity.
Meaning what?
Meaning you aren't managing a million lines of code. You might only be writing 15 lines. But the internal logic, the precise micro movements of pointers and data within those 15 lines is unimaginably dense. Defensive abstraction won't help you here. You can't just hide it behind an API. You need offensive abstraction.
Offensive abstraction, meaning we have to actively attack the logic.
Yes, drawing the mountain range or visualizing the stretching caterpillar, these are offensive abstractions. It is a mental scaffolding. It is a custom cognitive patch that you manually apply to your own brain to expand your working memory.
I see.
The disconnect happens because universities are essentially institutional factories designed to teach industrial standards. They do not teach cognitive patches.
But wait, the professors who write these legendary textbooks, the ones teaching at MIT or Stanford, they must know this, right? When they look at a rotated array, they are seeing the two parallel lines in their heads. They aren't running the simulation drop either.
They absolutely see the lines. They see the geometry so vividly and so naturally that they fall victim to a very well-documented psychological trap. The curse of knowledge.
The curse of knowledge, where you understand a concept so deeply for so long that you literally lose the ability to imagine what it feels like to not know it.
Exactly. The professor stands at the chalkboard, and because the geometry is just an automatic subconscious reflex for them, they don't even think to explain it.
They skip the foundation.
Instead, they write out dry, incredibly rigorous mathematical proofs using sigmas and limits. They do this because mathematical notation is the academically accepted, peer-reviewed language of their field. But in doing so, they completely leave out the movie playing in their head that actually makes the proof comprehensible.
They give you the script of the movie, but in a foreign language, and they refuse to show you the actual film. That is wild. But let me challenge this a bit. Is this merely an oversight? Is it just a byproduct of bad pedagogical habits, or is there something more systemic going on here? Because the sources hint that this might actually be a feature of the system, not a bug.
If we look closely at how elite institutions function, we arrive at a rather stark conclusion. It is an intentional feature of the filtering system.
A filter, so they aren't even trying to teach, they are trying to weed people out.
Consider the environment of a high-pressure coding interview at a major tech company, or an algorithmic competition, or a final exam at an Ivy League school. These mechanisms are incredibly expensive and time-consuming to run. They are not designed to teach you how to think in that moment. They are designed to filter a massive pool of applicants down to a tiny, tiny fraction.
Then who are they looking for?
They are actively searching for the specific subset of people who, usually entirely by accident, manage to develop this right brain translation mechanism on their own.
So they are looking for, like, the kid who played thousands of hours of spatial puzzle video games, or the student who double majored in physics and naturally maps data to physical space. And they just filter out everyone else who is just trying to read the text.
Exactly. If a textbook explicitly taught everyone the 5-minute no-code rule, and explicitly showed everyone how to draw the caterpillar and the mountain, it would ruin the test. It would level the playing field and the filter would break down. The entire system relies on the implicit assumption that if you can't read a wall of raw, abstract math and instantly understand it, you just aren't smart enough.
When the reality is you just haven't been handed the cognitive patch, that is simultaneously infuriating and incredibly liberating. Because if you are listening to this, it means your failure to grasp complex topics isn't a hardware issue with your brain. It's literally just a software issue.
Right.
You just need to install the right brain translator. And this is where the sources get truly expansive. We are moving beyond just code now. How does this translation ability apply to the rest of our lives? How does it help someone sitting in a corporate office or dealing with interpersonal drama?
Well, the foundational skill we are discussing here is the capacity to ignore details and retain properties. That is the purest definition of high-level abstraction. And once you master that, it applies universally to everything.
The notes provide a brilliant example of this for business executives, calling it black box thinking. Let's map this out for the corporate world.
Imagine the cognitive load of a CEO at a major multinational corporation. If that CEO attempts to look at the exact lines of code a junior developer is committing, or tries to listen to the specific conversational tactics a sales rep is using on a cold call, they will drown.
Oh, instantly.
Those are the microscopic details.
Yeah.
It is the corporate equivalent of simulation drop.
They are trying to be a human debugger for a 10,000-person company. It's impossible.
Exactly. To survive, a competent executive must view entire departments as a black box. Let's take the sales department. The CEO does not care about the internal state of that box. They only define 3 structural properties.
What are they?
First, the inputs. What is the quarterly budget and what is the specific product being sold? Second, the outputs. What is the total revenue generated? And third, the guarantees, or the invariants. The department must maintain a 40% profit margin no matter what happens inside.
So whatever chaotic interpersonal drama is happening inside that sales team, whatever specific software they use, whether they like each other or hate each other, all of that is aggressively ignored by the CEO's cognitive model.
By retaining only the structural properties, input, output, and margins, the executive can manage massive, sprawling complexity without their working memory crashing.
I love how cleanly that translates, but the sources push it even further into the messiest domain of all, our personal lives and emotions. They introduce a concept called state machine thinking.
This is fascinating.
Yeah, this is the idea of taking raw emotional complexity and translating it into mechanical physics. I was thinking about this, and I came up with an analogy based on the framework in the notes. Let me test this on you.
Please, let's hear it. I'd love to see how you apply it.
Okay, let's say I'm in a meeting and a coworker suddenly snaps at me over a really minor issue. My default left brain reaction is to instantly get lost in the syntax of the details. I will analyze their exact tone of voice. I will replay the specific adjectives they used. I will sit there processing my own hurt feelings, and my brain will start spinning this massive, complex narrative about how they must have secretly hated me for years.
Which is an exhausting amount of cognitive load.
Exactly. It's exhausting. But if I apply state machine thinking, I have to zoom out and view my coworker as a mechanical system. I stop analyzing the words, and I look for the structural triggers. I say, my coworker is currently operating in the anxious state. Why did they transition into this state? Because the quarterly budget cut trigger was just pulled by senior management.
Oh, that's brilliant.
The invariant property here isn't that they hate me. The invariant property is that they are structurally incentivized to protect their departmental KPI.
That is a masterful application of the framework. You have taken a situation that felt like a deeply personal, chaotic attack, and you have stripped away all the emotional syntax. You mapped the underlying mechanics. You literally turned a social conflict into a predictable physics problem.
It fundamentally changes how you experience stress. It makes everything so much quieter.
And the sources actually provide a tool to deploy this in real time. Whenever you feel that overwhelm, whether it's code, a business decision, or a personal argument, you must aggressively ask yourself 3 questions. What are the boundaries of this system? What are the constraints acting upon it? And what is the invariant, the one thing that absolutely never changes? Answering those 3 questions creates a semantic filter that just blocks out the noise.
Okay, so we have successfully hacked coding interviews, and we've mapped out emotional state machines. Now it is time to face the absolute monster. We are ascending to the peak of cognitive overload. Let's talk about the language of pure math, specifically calculus.
This is where the simulation drop is most universally feared.
Truly, millions of people have hit the wall of calculus and just given up on STEM careers entirely. Why does looking at a textbook page full of integrals or limits cause that exact same brain freeze as the LeetCode array?
The notes argue that the failure is almost entirely linguistic. It is about how we are taught to vocalize the symbols. When a student sees an integral equation, they are trained to read it aloud, sequentially like a sentence. They read the integral from a to b of f of x dx.
Right, just reading the grammar left to right.
Yes, but mathematical notation was never intended to be read like a novel. These symbols were invented by absolute geniuses over centuries as a way to compress incredibly rich, multi-dimensional visual movies into tiny, ink-saving text shortcuts. They needed a way to write down a massive geometric concept quickly.
But the educational system, suffering from the curse of knowledge, forces us to memorize the text shortcuts and completely forgets to show us the movie that the shortcut represents.
Precisely. So our task is to take calculus and translate it back into the visceral, physical movies it was always meant to be. Let's start with the definite integral.
Okay, the classic definite integral. The big, stretched-out S shape that haunts high school students everywhere.
Most people see that S-curve and immediately panic because it looks alien. But don't see a shape, see a physical action. The integral sign historically stands for sum, but in our mental movie, we're going to translate it as the command to add them up frantically.
Frantically adding what?
Let's look at the terms inside the integral. We have vortex multiplied by integral. If you try to hold those as abstract algebraic variables, you fail. So let's make them physical. Visualize 5x integral not as a mathematical function, but as the physical height of a single cooked strand of spaghetti. It's a noodle standing straight up on a table.
Okay, a very tall, thin noodle representing the height of the graph at one specific point.
Now, what is edazile? In calculus, edageiz represents an infinitely small change in x. But physically, in our movie, it represents the width of your noodle. It is an unimaginably microscopic sliver of width. So when you multiply the height by the microscopic with Dickonomic psi, you get the physical area of that one single noodle.
I'm tracking perfectly. I have the area of one microscopic spaghetti noodle.
Now, bring back the integral sign, evaluated from point A to point B. Imagine you are physically holding a wide paintbrush. The integral is the sweeping action of your arm. You are wiping that paintbrush across the canvas from point A to point B, and as you sweep, you are frantically welding an infinite number of these microscopic noodles together side by side to paint a solid, unbroken two-dimensional area.
That is stunning. I'm no longer doing abstract algebra, I am painting with noodles. The terrifying symbols are literally just the choreography instructions for my paintbrush.
Exactly. Once you see the movie, the math becomes docile. Now, let's consider the counterpart, the derivative. Most people who took calculus just memorized that a derivative is nu a over zeros, or they memorized a bunch of mechanical power rules to pass a test.
That was totally me. Bring down the exponent, subtract 1, pure syntax, 0 actual understanding.
But the movie for a derivative is intensely physical. It is a seesaw. A derivative is a question of physical leverage. Think about a seesaw resting on a fulcrum. The delta, the change in x, is the amount of physical effort you are putting in. How hard are you pushing down on your end of the seesaw?
Oh, yeah.
And the delta y is how much the world or the system pushes back. How high does the other end of the seesaw go? A derivative is just asking, at this exact microscopic moment in time, what is the precise exchange rate between my effort and the universe's reaction? If the derivative is high, you have incredible leverage. A tiny push from you sends the system flying. If the derivative is low, you are pushing a boulder.
It totally grounds everything in physical resistance. But I have to push back again because the sources don't just stick to basic shapes. They introduce a really gnarly formula to test this visual theory. The noodle painting makes perfect sense for a basic area under a simple curve. But what happens when the formulas get messy and convoluted? They bring up the expectation formula from statistics and probability.
Yes, the integral is $6 multiplied by FSDXE. It is a notorious stumbling block in stats courses.
If I look at that, my brain defaults to blind algebra. I understand that VIO x dxd is the area of my microscopic noodle, but now the formula demands that I multiply that noodle by $6, which is its position on the horizontal axis. How do you visualize multiplying a physical noodle by a physical distance without just giving up and doing the math on paper?
This is exactly where the physical metaphor proves its ultimate power. If you trust the physics, the answer's right there. Let's walk through it. You already established that def x dxd as the physical area, or let's say the physical weight of that specific noodle.
Right.
And you know that $6 represents the physical distance of that noodle from the center point, the fulcrum.
Yes.
So I ask you, in the real world of physical mechanics, what happens when you take a weight and you multiply it by its distance from a pivot point?
Weight multiplied by distance?
Well,
Wait, if I have a heavy weight on a long stick, that's leverage. No, it's turning force. That's torque, like using a long wrench to turn a bolt.
yes, it is torque.
Yeah.
By applying that physical reality, the entire intimidating statistical formula transforms. $6 is the length of the wrench arm, and featherless D is the weight pushing down on that arm. Position times weight is torque. So when you are looking at the expectation formula, you are not calculating some abstract, ethereal statistical probability. You are conducting a physical search. You are summing up all the competing torques to find the exact center of gravity.
You were trying to find the balancing point of the entire shape.
Precisely. If you took the probability distribution graph, printed it out, and cut the shape out of heavy wood, the expectation value is the exact literal coordinate where you could place your finger and balance that wooden shape perfectly without it tipping over. When you see that formula, you shouldn't see algebra. You should feel the shape balancing on your fingertip.
That completely reorganizes how I will ever look at a statistics equation. It's profoundly elegant.
Okay, Let's keep ascending. We've conquered code, we've conquered calculus. Let's step into what the notes call the space portals. We are talking about matrix math and linear algebra. If calculus is about noodles and seesaws, what went wrong with how we learn linear algebra? What went wrong is arguably the greatest pedagogical failure in modern mathematics, the row by column teaching method.
Oh, the trauma is flooding back. Take the first row of matrix A, multiply it element by element with the first column of matrix B, add all those little products together, and then write that single number in the top left corner of a new box.
It is the ultimate working memory killer. It is a recipe for instant simulation drop. You're asking a human brain to track horizontal movement across a row, simultaneous vertical movement down a column, perform multiple independent multiplications, hold those products in temporary storage, and then sum them together. The biological hardware snaps in seconds. It is a completely unnatural, mechanical way to think.
So we need to throw away the grid puzzle. What is the right brain visualization for a matrix?
The sources provide two incredibly powerful metaphors. Metaphor one is action-oriented, the space portal.
Build the portal for me.
The fundamental error is viewing a matrix as a static, dead box of numbers. A matrix is not a container. It is an action. It is a machine that does work. Imagine a simple vector, a little arrow pointing to a specific coordinate in 3D space. When that little arrow steps into the portal of a matrix, it experiences intense spatial special effects. The portal might stretch the arrow out to be twice as long. It might rotate it 90 degrees. It might squish it completely flat against the floor.
So the matrix is a verb. It does something to the space.
Exactly. So what does it mean when the textbook asks you to multiply two matrices together? Say matrix A times matrix B. It is not a grid multiplication puzzle. It is simply a chain reaction of special effects.
Walk me through the chain reaction.
Imagine your little vector arrow. First, it walks through portal B. Inside portal B, it gets stretched out and turned blue. Then immediately after exiting, it walks straight into portal A, where it gets rotated upside down and squished.
Okay, so it suffered two distinct transformations in a row.
Yes. And the mathematical result of quad odd D by BB is simply the creation of a brand new single portal that combines both of those effects perfectly. If another vector walks through the new wamid odd BB portal, it will be instantly stretched, turned blue, rotated, and squished, all in one single step. You aren't calculating rows and columns, you are choreographing a sequence of spatial transformations.
I can actually visualize that in my head without doing any math. The second metaphor the sources provide is more visual-oriented, focused on construction. They call it the recipe and the toolbox.
This metaphor is crucial for understanding how matrices actually build objects in space. Imagine you are looking at a standard matrix multiplication. A matrix on the left, multiplying a vector on the right. Think of the large matrix on the left as your physical toolbox.
Okay, a heavy metal toolbox.
Open it up. Every single column inside that left matrix represents a specific fundamental base tool that you own. Maybe column 1 is a hammer, column 2 is a saw, column 3 is a wrench. These are your raw materials.
Got it. The left matrix is my inventory of tools.
The vector on the right, the thing you are multiplying by, is not a toolbox. It is your recipe card. It contains pure instructions. It looks at your toolbox and tells you exactly how much to stretch and combine your base tools to build something new. The recipe card says, take 2 units of the hammer from column 1, add 5 units of the saw from column 2, and subtract 1 unit of the wrench from column 3.
So matrix multiplication is just following a set of instructions to mix a specific cocktail of columns together to bake a brand new coordinate in space.
Precisely. You are mixing base ingredients. Now, why should a listener care about space portals and toolboxes? Because this isn't abstract theory. This is the literal architecture of the modern digital world. If you understand these two metaphors, you understand how reality is rendered. Let's start with 3D gaming.
How does the portal map to a video game?
If you are playing a visually stunning 3D game and your character waves their arm, the game's engine is not manually calculating the individual physical path of every single pixel on that arm. That would melt the processor. Instead, the game engine creates a rotation matrix, a space portal. It takes the entire geometric structure of the arm, shows it through the rotation portal, and instantly calculates its new position relative to the world coordinate system. Every movement on your screen is just geometry flying through matrix portals.
And the sources take this to the absolute bleeding edge of technology today. They connect matrix multiplication directly to artificial intelligence and large language models, the architecture behind things like modern chatbots.
Yes, this is perhaps the most profound application. At the very heart of these neural networks are unimaginably massive matrix multiplications. When you type a prompt into an AI, the system does not understand English. It takes your words, converts them into vectors, little arrows in space, and throws them into a massive, multi-billion parameter high-dimensional sieve. And that sieve is just a matrix.
What a semantic sieve.
Exactly. The matrix multiplication is literally testing the geometry of language. It is stretching, rotating, and mixing concepts in thousands of dimensions to see how strongly different words align with each other in abstract space. It measures the physical distance between the concept of king and queen. Understanding matrices as space portals and recipes gives you an intuitive, visceral grasp of how AI actually thinks and generates text.
It removes the magic from AI and replaces it with magnificent geometry. Okay, we have reached the summit of our deep dive, segment 7. The notes call this the final boss. We are stepping into the realm of quantitative finance, hedge funds, and Wall Street. We are looking at stochastic calculus and Ito's lemma.
This is where we tackle peak mathematical complexity. This is the exact math used to price exotic options and manage billions of dollars of risk in global markets. And it is notoriously difficult.
The notes introduce a specific, terrifying rule that sits at the very heart of stochastic calculus. For anyone who remembers basic calculus, you learn that a tiny change, a seventile or an everyday twee, is microscopic. And if you take a microscopic number and you square it, it becomes so infinitesimally small that it essentially vanishes. It equals 0.
That is the foundation of smooth classical calculus.
Right. But the sources point out that in stochastic calculus, the fundamental rule is $$ squared equals $, meaning if you take the microscopic change in the randomness, the $, and you square it, it doesn't vanish. It actually perfectly equals dollars, which is the steady forward flow of time itself. To my left brain, that sounds like pure magic. Why doesn't the squared change disappear?
To understand this, we have to look at the visual, physical difference between normal textbook math and the reality of the stock market. Normal calculus assumes that the universe is fundamentally smooth. If you look at a parabola and you zoom in close enough, the curve flattens out and looks like a perfectly smooth straight line.
Right. If you zoom in enough on a circle, it looks flat.
But stochastic calculus deals with Brownian motion. This is pure, unadulterated, random, chaotic movement. It's the exact mathematical model of a violently volatile stock market. And the key property of Brownian motion is that it is a fractal. If you look at a jagged stock chart and you zoom in on a single minute, it doesn't become smooth. It is still jagged. If you zoom in on a single second, it is still jagged.
It is a line made of infinite, hyper-sharp golden teeth, as the notes beautifully describe it. It is jagged all the way down to infinity.
Exactly. It vibrates violently up and down, continuously and infinitely. Because of this infinite jaggedness, it possesses an extraordinary amount of physical energy. If you take those microscopic, violent up and down vibrations and you square them, their accumulated energy doesn't vanish into 0. The sheer volume of that microscopic chaos accumulates perfectly to equal the steady forward flow of time.
I want to repeat a quote from the notes because it is so poetic. Fluctuation energy settles into the hourglass of time. The literal chaos of the system is what powers the forward movement of the clock.
It is a profound realization about how randomness interacts with reality. And this realization builds the foundation for the ultimate equation of our deep dive, Ito's lemma.
If you look up Ito's lemma on the internet, it is a massive, multivariable partial differential equation. It is a wall of Greek symbols that makes graduate students weep. But we are going to honor the 5-minute no-code rule. We are going to deconstruct Ito's lemma into a 3D movie. No symbols, just physics.
Let's build the movie. I want you and everyone listening to imagine that you are holding a curved, beautifully crafted Chinese porcelain bowl in your hands.
Okay, I am physically holding the bowl.
This physical bowl represents your derivative portfolio. It is your financial position in the market. Now look inside the bowl. There is a heavy marble resting in it. This marble is the stock price. And because the market is driven by Brownian motion, this marble is not sitting still. It is vibrating violently, bouncing chaotically in every possible direction at incredible speed.
Okay, my hands are vibrating from the force of it. The marble is going absolutely crazy. Now, let me pause the movie and ask a logical question. If that marble is moving purely randomly, meaning it has a perfect 50-50 chance of bouncing to the left or bouncing to the right, shouldn't its overall effect on the height of the marble inside the bowl just cancel out to 0? It goes up a bit on the left, it goes up a bit on the right, but on average it just nets out to nothing.
Your logic is flawless if we're using normal calculus. Normal calculus looks at the average and says, left cancels right. The net expected change is 0. But that is precisely where normal calculus fails, and where the Ito correction, the genius of this math, steps in. This is the magic of the bowl.
Show me the magic. I am holding the bowl.
Pay attention to the shape of what you are holding. You are not holding a flat plate, you are holding a bowl. The walls of the bowl curve upwards. In quantitative finance, they call this upward curvature convexity, or gamma.
Upward curvature, gamma. Got it.
Because the walls curve upwards. Think about the physics of the marble. If the marble vibrates violently to the left, it doesn't just move laterally. Because the wall is curved, it rolls slightly up the wall. It gains physical height.
Okay, it rolls up the left side.
Now, what happens if the marble vibrates violently to the right?
It hits the right wall, and because that wall is also curved, it rolls slightly up that wall too?
Exactly.
Uh-huh.
This is the breathtaking insight of Ito's lemma. Because the environment is convex, direction no longer matters. Whether the marble goes left or right, it is forced upward by the geometry of the bowl. The violent side-to-side vibration, combined with the curved walls, creates a permanent unidirectional upward lift on the average height of the marble.
That is incredible. The left and right movements average out to 0, but the up and up movements accumulate.
Pure chaos generates a net positive lift.
And the notes explicitly state that this physical reality is the entire basis for a major Wall Street strategy. This is why quantitative traders say they go long gamma.
Yes. When a multi-billion-dollar hedge fund goes long gamma, what they are fundamentally doing is buying the curved porcelain bowl. They construct a portfolio of options that creates an upward convex geometry. And they do this knowing that the stock market will behave like a violently vibrating marble.
So they don't even care if the stock market crashes or surges. They don't care if it goes left or right.
They do not care about direction. They only care about volatility. They just need the marble to vibrate violently. Because if you own the curved bowl, pure chaos and volatility automatically pump money into your account. The math proves that the fluctuation energy will force the value upward.
They literally weaponize chaos using geometry. They aren't predicting the future. They are just building the right shape to capture the energy. It all comes back to shapes. From cutting an array in half on LeetCode with the caterpillar, to balancing noodles on a seesaw for calculus, to buying porcelain bowls on Wall Street, it is all the exact same cognitive trick. It is about stripping away the intimidating symbols and seeing the physical structural world underneath.
It is the ultimate cognitive unlock. Once you learn to see the geometry, the paralyzing fear of complexity simply vanishes.
Which brings us to the end of an incredible journey. We've traveled from the simplest arrays to the terrifying heights of stochastic finance. And the central, undeniable takeaway from all these sources is this. True, deep understanding is never about memorizing syntax. It is never about brute-forcing equations in your limited working memory. It is about stripping away the heavy clothing of mathematical and programmatic symbols to reveal the geometric moving physical reality that those symbols were invented to describe.
And if you are listening to this right now, and you have ever felt overwhelmed by a dense textbook, or paralyzed in a coding interview, or confused by a complex corporate dynamic, I want you to remember, you are not bad at math, and you are not bad at coding.
You've just been trapped by the curse of knowledge. You've been forced by a filtering educational system to use your left brain's sequential text parser to do a right brain's multidimensional geometric job. You have permission, starting today, to ignore the text. You have permission to take 5 minutes, grab a blank piece of paper, and draw the pictures.
Build the mental scaffolding. Give your brain the physical tools it desperately wants to use.
Exactly. Now, before we sign off, I want to leave you with one final, deeply provocative thought to mull over based on everything we've uncovered today. We've spent this entire time actively turning abstract math and code back into physical, real-world metaphors. Space portals, stretching caterpillars, balancing noodles, and bouncing marbles, all just to help our squishy human brains comprehend them.
A necessary cognitive translation.
But consider the reverse of that idea. If advanced mathematics perfectly describes physical reality, is it possible that the physical universe around us, with all its chaotic, bouncing marbles, gravity wells, and stretching space-time portals, is actually just a giant running algorithm? And if reality itself is just math executing in real time, what invisible code are you executing right now without even realizing it?
That is a phenomenal question to sit with.
Thank you so much for taking this deep dive with us. Wherever you go next, keep questioning the symbols, trust your visual instinct, and always look for the geometry hidden just beneath the surface.